All right, so let's, well, there we go. I couldn't get it to work. All right, so chapter 6. Briefly, we're going to talk about what a centroid is, get into the introduction of that concept, talk about centroid fundamentals. Uh, Mathematically, there's a lot more to it if you want to read, like, how it's developed, but in terms of what we're going to be dealing with, you don't need to know that much. It's really just kind of formulamatic. And then finding the centroids, we're going to be looking at two ways of finding centroids today. One is what I just call simple shapes, and then compositing them together, bringing simple shapes together. And the other one is what you would call manufactured or engineered shapes. And those are going to require you to refer to your appendix in the back of the book, Appendix A. So you are going to need to have those charts available. And all you need to do with that, a couple of formulas and a simple calculator, you can get this stuff calculated pretty easily. So then we'll look at, like as we said, composite shapes and manufactured shapes. Okay? So this probably won't take us too long, but I want to go through at least 3 examples today and get you guys started on the homeworks. Okay, so basically when you hear the term centroid is just what you might consider the center of an area. Okay, so if we look at the center of gravity in a 3-dimensional body, that's an important process, and sometimes we call that the center of gravity. I'm sure you've heard that term before, but this is where the resultant force of the gravity goes through the body and it acts on another body. So we can define the location of that by an x, y, and a z location with respect to any random origin. So that origin can be out on a corner of the part, it could be off of the part, it could actually be right in the center of gravity point itself. And if it is there, then you have 0 centroid location x, y, or z. So this is important because to know where that center of gravity is, it's really important when you start to look at structures, how that stuff will act on a structure, where the weight is acting through that structure, and those kind of things. And this also will determine, or could help you determine, where the optimum point of support would be to give you optimum equilibrium. So when we think about that, these are all important consequences. You guys have all probably been canoeing, I'm sure. And if you're familiar with a canoe, they're pretty floppy. And if you stand up very often, because you're raising your center of gravity with respect to that, very often you're going to just fall over and get swamped. So you can see where center of gravity is important. Same thing with like a vehicle. When you're driving down down a road, if you have a vehicle that has a high center of gravity, it's got a real easy, it'll tip easy. So we kind of have to watch those kind of things. So if the 3-dimensional body that we're talking about with a center of gravity is considered to be very thin and basically infinitely thin, then basically you're bringing that 3-dimensional kind of shape down into what we would call an area. So instead of dealing with a volume, now you're basically dealing with an area. So when you hear the term centroid, we're really talking about an area, not a volume. So center of gravity is more applied to volume. So the location of the resultant in the plane is referred to as that centroid of the shape. Okay, and each shape would have its own centroid location. And the centroid location is basically an x and a y value, as we'll see. And that's what we're going to be after, solving where is the centroid of that area. So I'll give you a picture here in a sec, but centroids of areas are going to be extremely important for structural design, and we're going to see how this comes into play. But when we talk about what we call bending of objects, you're going to see that the centroid typically passes through that axis and they typically call that a neutral axis. So to give you an example of what I'm talking about here, let me flip over to my screen. Let's see. Okay, so if we look at, let me draw a simple shape here. So if I have a beam that's simply supported, whoops, that didn't work. So if I have a simply supported beam, and you've got a, I'm going to just make it roller on one side. Okay, running through this about the center point, and that's not always the center, but let's just envision that kind of being center. If you push a load down on this thing, what will happen, what we were just talking about there, let me see if I can get if I push a load, so this is getting a little bit off the subject, but what I just kind of want to show you is if we put a load right here, this beam is going to want to tend to bow, okay? And so what will happen if we look at in the cross section, try to give you a, so this is a cross section of this in length. What's happening, you got that neutral axis, or what they call a, what's happening when you push on this, in the top here you're under compression, and then the bottom here you're under tension, because the fibers want to push together here, and they want to pull apart here. What's happening about this line is typically nothing, neither compression or tension. So you may have compression at the top and tension at the bottom, but nothing right at this line. And this line is basically your, what we call the centroidal axis. So this is where centroids become very important. Now, this centroid, depending on the shape of this right here, may shift up this way or it may shift down that way. So it's not always exactly in the center, depending on the shape we're talking about. Okay, so that gives you a little bit of an idea what kind of they were talking about back here. Okay, so that's why we're saying bending in a homogeneous object will tend to occur about that axis that passes through the centroid, and that's what I was just trying to explain there. We're going to get into that more when we get into chapter 12 as we see, beam design. So that'll be an important concept. So centroids, we're going to learn how to do them here, but you're going to be utilizing them a lot more as we get into other things in the strength of materials section. So we said a centroid is the location where the gravitational resultant will act in a homogeneous area. What that homogeneous means, it's a material that's not a composite material. It's one type of material, like say just concrete or wood or something like that. It doesn't have any other things in it. So the centroid for any area is, you can think of as just the balance point of the area. And the easiest way to think about that is if you took, let's say you took your book and you tried to balance your book on your finger, you guys would all go right to what you would call the center. And I might find that by taking a rectangle and I could just simply draw two diagonals. So here's what I'm saying. Let's go back over here a minute. So again, if I look at this, right here, if I ask you to find that, let's say that's your book, you're looking at that, and I ask you to find the center of that, the easiest way to do that would probably be to draw a diagonal from one corner to the other. So I draw a diagonal from that corner to that corner. Got to hit the corner. And if I draw a diagonal from corner to corner this way, that would be the point where you're putting your balance. Okay. Now again, a book is three-dimensional, but if we reference that to two-dimensional, then you'll see what I'm talking about. So that's what we would think of as the centroid. But when we get to the actual centroid, what we have to do is tell somebody where to find the centroid, not just doing it this way. Okay, so that's what we're going to look at. So that balance point is located typically by an x value and a y value distance from some defined origin or axis. Okay, so it really, when we talk about centroid, it's two distances. Okay, two distances along an axis. So it's just basically like an x coordinate and a y coordinate to that point on the figure that you're looking at. And a centroid is defined by what they call the x bar distance to the YY centroidal axis and the y bar distance to the XX centroidal axis. So let me go over what I'm talking about here, because those terms are a little bit sketchy until you kind of figure out what's going on here. So let's take a look at this. And so if I have an origin, let's say my origin is right here. So then if that's the case, I have a axis. So I have an axis that's running this way through my origin. Now my origin happens to be on the part, and that's not always going to be the true case here, but usually we put it on the part. And I have an origin right here. That's my y-axis. So if we call this the y-axis, and we call this the x-axis, and this is my origin, my centroid, I'm just going to put it out here. My centroid is out here. So what we have this would be called the YY centroidal axis. This would be called the XX centroidal axis. So we'll call that the XX centroidal axis, the YY centroidal axis, and the distance from the origin to the YY centroidal axis is labeled as X bar, and the distance from the origin to the XX centroidal axis is Y bar. So there's your Y centroid, and there's your X centroid, and this is the actual centroid itself. Okay, so that's our terminology. We have an origin, and we have a YY and XY, XX centroidal axis, and then we'll have that X bar distance and Y bar distance. Okay, so we're going to see a lot more of that as we get into this today. Okay, so centroids of simple shapes have been determined, and you can find those. You can find those on a table in your book. In table 6-1 on page 190. So if we look at that, you'll see we have 4 very simple shapes in there. And if you notice, what the book is showing you is that for a simple shape, they show you where the origin is, and you have to pay attention to that when we get into this kind of thing. So look at the first shape there. You see the rectangle. Notice where the origin is in the lower left corner, and they give you what's called a B value and an H value. So if your B is parallel with the x-axis in that point, you can see that your X bar distance is going to be half of the base. So that's pretty standard. And then the same thing with the H. So you have to, when we look at these problems, you're going to have to reference this chart, and then you're going to have to reference how that works with where your origin is. Okay? And we're going to do a couple of problems with this, so it's not a big deal. The triangle is probably one of the hardest ones to deal with, and the half circle. So I'm going to show you kind of how those work. Let me see if I got those on here. I don't think I do. Okay. Well, we'll come back to that. So we're going to look at that chart here in a minute. But this is what I just drew on that board for you a little bit. So you can notice if we have our simple shape here, we have our simple shape of our, in this case, it's a very simple circle. The origin of a circle is the center point of the radius, obviously. Notice I have an origin out here. So the origin doesn't have to be on the part at all. And in fact, it can be floating way out. But if you pass the y centroidal axis through that centroidal point and the x axis through that, you're measuring the distance x bar and y bar to those. All right, so do keep in mind, we can put the origin anywhere, okay? And in fact, the origin, instead of being here, where these values are positive, could be over here. So you can have negative values of centroidy and centroids. Just depends on where your origin is. Okay, so when we look at determining centroids of standard geometric shapes, we just directly look at that table. So again, it's just very important to determine where the origin is, because just because you have a triangle doesn't mean you're going to always use it the same way with that chart, okay? So it's very important to understand how that works with respect to that. So you kind of have to turn that chart to match the situation, what's going on with you, okay? Is everybody okay with that? Yeah. Okay, take that as a yes. So let's consider this right triangle. We have a right triangle that has what I'm calling a base of 12 and a height of 5. Okay, now, if we rotate that triangle 90 degrees, this could actually be the base, and that could be the height. So that's going to be an issue. So if you look at that chart, that table on page 190, you'll see that the centroid, if the origin is located over here, okay, with respect to the way that chart's drawn, it is for the height, for the area, it's going to be base times height times 1/2, or 1/2 the base times the height. So area is going to be important, because as we get into the composite centroids, you're going to need them. But if you just have a simple centroid like we do here, all we need to do is look for the x bar distance and the y bar distance on that chart. So you'll notice that if I want to find the centroid, which is somewhere over here, it is 2/3 of the base distance. So that's saying from this end, it's 2/3 over. And that will give me the y centroidal axis. And notice that the h, or the y bar from the origin down or up is 1/3. So again, if we rotate things, that's going to make a difference. And triangles are always tough, but here's a good way to remember them. The centroid is always 2/3 from the small end or 1/3 from the big end, where I'm talking that is the small end and this is the big end, okay? So again, let me say that again. 2/3 from this end, the small end, I'm sorry, yeah, and 1/3 from the big end. Now, if we're looking at this way, it would be 2/3 this way or 1/3 this way, okay? So let's take a look at that in successive slides here. So here's an example. Notice how your centroid value is going to change with origin and location, looking at what we would call case 1. So this is exactly what you're seeing in the book. You see that this is my origin. So through my origin, I'm passing an x and a y axis. This represents, that symbol represents where my centroid is. So we know this distance is 12, right? So from that example, if you take 2/3 of 12, so if you take 12 times 2 divided by 3, you get 8. So it's telling me that the centroid to the y centroidal axis, the x bar distance, would be 8. In this case, inches or meters or millimeters, whatever unit you're in. And because we're going in this direction from the origin, we're going to be 1/3 from the big end. So 1/3 of this total 5 gives me the 1.67. Okay, so that's pretty simple. But if we rotate things, okay, if we rotate things and say, now this is the origin, now what's going on, we're not going 2/3 of this distance, we're going 1/3 over. So we take 1/3 of 12, that gets us the 4. And again, this doesn't change. So notice orientation of this is all important. And the other thing to remember, no matter how you orient it, the area is always going to be the same. So area will never change, but centroid location can definitely change with respect to where your origin is. And if that origin was off of that part, then that makes it a little bit more challenging. And we're gonna look at a couple of cases. Is everybody following me so far?
Yeah.
Yeah.
Okay. It gets a little sketch. Like I said, triangles are probably the hardest ones. You guys will find that out. and the other one is that half circle. People always have troubles with those two things, but we're going to piece them together and see, and you're going to have plenty of chances to work through these. So I'll give you that homework, and then we'll work through them through the Wednesday, and then Thursday we'll get into those. That's what we're going to be looking at. Let's look at the last case. Notice this one now completely changes things up, because now I'm saying, okay, I've rotated the triangle 90 degrees, same triangle, same area, same base and not what we called base, but this is now 5 and that's 12 going this way. But notice I'm putting my origin here, and so we're looking at this one now. So the x-bar distance is 2/3 of this 5, and that's where we're getting 2/3 of 5 is 3.33, and we're coming up 1/3 of 12, and that gives us the 4. So you can see in each case for the same exact triangle, depending on its orientation and its origin point, you're getting 3 different centroids, okay? So that's the thing to keep in mind. There is not just one magic centroid for any shape, all right? So basically, you can think of a centroid as the location where a moment created by a total area is equal to the sum of moments created by incremental pieces. And they kind of express it like this, that A, which is your total area, times your x bar, is going to be equal to the sum of the little incremental a's and x's, and A of the y bar is equal to the sum of the incremental a and y's. So again, let's take a picture over here, show you this real quick. The reality is that it's not going to be that tough to actually have to deal with that, but let me kind of clean this up a little bit. So what we're saying is if this is our centroidal axis, and you got a little part out here, a little piece out here, I'm just going to put it right there. You can measure this distance, which we would call y, times the incremental area, not the total area, just the little incremental area of that part. And there's one on the other side. If you go the same distance, basically you're saying the moment on this side has to be equal to the moment on that side of the centroid, so that's balanced. And what you're doing is you're doing that incrementally all the way up and all the way down. So y is a distance, a is an area, so basically you have a moment. Okay, instead of a force, you have an area times that. So it's kind of like a moment. You know, a moment is a force times a distance. We're kind of looking at this as an area times a distance. So that's kind of what they're talking about there. Okay, so don't get too involved in that, but you can kind of see what's happening. But this equation is going to be important, as we're going to see here in a minute. Okay, so x bar is the distance from the origin to the yy centroidal axis. Y bar is the y distance from the point of origin to the x centroidal axis. A would be your little individual pieces of area, and A is your total of all areas. Okay, so again, we're going to be utilizing this equation. We're going to see this here in a minute, how this pieces together. Okay, but the mechanics of doing centroids are really simple. They're not that big of a deal. Okay, so very often you don't have a simple shape like a square or a triangle or a circle or a half circle. So you piece these together in what we call a composite. And if you have a composite shape, what you're going to have to do is deal with each individual composite with its centroids and then kind of add this stuff together. Okay, and shapes that are composite are more common than just the simple shapes. Okay, so it's important to determine those. And we have two types of composite shapes. We'll talk about what I would call just simple figure composite shapes and then manufactured composite shapes. Okay, in particular, when we get, like we said, into bending in chapter 12, this becomes a lot more important. Okay, so the process of finding centroid of a composite shape, it's very straightforward because you're going to use a step-by-step process, and we create a little table that allows us to do this. If you look on your 6.1 table, they show you a way of doing that, but I'm going to run you through the example here. And we're going to do this for combined standard shapes, which I'm going to run you through a couple of examples, and we're going to do it for a manufactured shape or two. But this is going to require you to reference Appendix A in the back of the book. Okay, so we're going to look at that. All right, so here's your process for finding a composite shape, whether it be a manufactured shape or a simple shape. It's pretty straightforward. So the first thing is you're going to break the composite shape down into areas that you can handle. So what we can handle right now is just 4 shapes, basically rectangle, triangle, circle, and half circle. Now you could look up probably on the internet or other places and find formulas for centroids of other shapes, but we're not going to see anything other than those 4 shapes, and not all of those every time. Okay. Then you're going to choose a point of origin if one is not already given. So normally on these problems, they're going to tell you where the origin is, because if we don't do that, then everybody could have different answers based on where you choose your origin point. Okay, so we're going to have an origin and then define an x and a y axis, and that origin is where you're going to get your x bar distance and your y bar distance. All right, so we construct this table, and this table is broken down into the shape that you're considering, the area of each shape, respectively. X is the distance from the origin to that shape's YY centroidal axis, and then you would take the area times the X and put that in this column. And then you're going to have the Y distance, which is the Y bar distance from that shape's origin to that point. Then you multiply the area times that. When you get done with each area, with each shape, you're going to sum the total areas. You sum the total AX values and sum the total AY values. Now, a word about this, which is important, the X values can be negative as well as positive. Same thing with the Y. Area can typically be both positive and negative as well. So if you have what we call a voided area, like say where you've drilled a hole, you consider that a negative area. So when you sum these areas, you could have negative area total, or you could have a large amount of area, but one negative, it's going to decrease that a little bit. These guys can also, when you multiply a negative area times a positive distance, you can have a negative AX. So you can have negative values in here, positive values in here, but the bottom line is you got to pay attention to that so that when you sum these, you're getting that right. Same thing with the Y, all right? And then the final step to solve your centroid is to sum those up, and then you'll calculate that distance by taking your sums of the one divided by the sum of the other. Okay, so with all your individual areas, you sum the A, you sum the AX, and you sum the AYs, and then you calculate the distance by taking those sums and using this. Your X bar distance is going to be equal to your sum of your A-axis divided by the sum of area, and your Y bar distance will be the sum of your AYs divided by your area. Okay? Now we're going to use this process, and we'll just go back to this chart. We will use this chart to do both composite shapes of simple shapes and composite shapes of engineered shapes. Okay, so we're going to take a look at a couple of examples. I don't know if I have an example on here. Okay, so let me jump in and do a couple of problems with you. Okay, give me a sec to set up. If you want to take a quick break real quick, it's going to take me a minute to break this up. So let me get this set up here. So I'm going to do a composite shape. Give me a sec to draw this thing up. Yeah, come on. I'm trying to move that a little bit harder to do than I thought. It's going to take me a minute to do this. Okay, so I'm going to have a half circle as part of this. Okay, so here's my shape, and what I want to do is find the centroid of that. And as we look at that, that looks pretty involved. Let me put some numbers here, because we're going to need to know geometrics. This process is all about geometry. Okay, so that's the one thing about it that's kind of important to understand. So I have a distance here, and I have a distance here, which would be the side of that line, but it also happens to be coinciding with the center of the circle. Okay, so there's those guys. Let me put this down here a minute. Got a distance here. And a distance here. So let's okay, so let's put some numbers to this. So this is 12 inches. And this is 6 inches. And that's 6 inches. Okay. So we know our radius is also 6 inches for this guy. Radius points about right there. So defining this as our origin over here, we're going to say that the x-axis and y, there's my y, and there's my x going this way. So notice we placed our origin out on that piece. So we need to solve this, but what you first have to do, what it says in the steps, is break that thing down into composite shapes that you can figure out. Can anybody see how we can break that down into composite shapes that are on that page 190 chart? How many shapes do we have here, guys, that we can handle?
3.
3. Okay, what do you see as the 3?
Just a rectangle, a triangle, and then just a half of a circle.
Okay. All right, so I'm assuming, Jacob, you're saying that triangle,
Yep.
rectangle, half semicircle, correct?
Yeah.
Okay, so there's another way you could actually do this. You could make this one big rectangle right here. So we see that?
Mm-hmm.
And have this little triangle as a negative triangle. Okay, so there's a couple of ways you can handle it. All right, but I agree with what you said. I've got shape here, here, and here. Does everybody else agree with that? That was really good.
Yeah.
Okay, so what I usually do, the first thing I do after I decide how I'm going to break it down and where my origin is, I'm going to assign these guys shape numbers because I need to be able to keep track of them in my chart. So I'm just going to we're going to call that shape 1, shape 2, shape 3. Is everybody okay with that? Okay, so we're ready to construct a chart, and we're going to have shape, and then we have area, and then we have the x distance, and then AX, and then the y distance, and then the AY distance. So you're going to get used to this chart because that's all this is going to be in this chapter. Okay, it's pretty simple actually once you get into it. So the first one is shape 1, and then we're going to have shape 2, and then we're going to have shape 3. Okay, so let's just operate on shape 1 first. Keep in mind that this is where my origin is, okay? So shape 1 is a rectangle that is 12 by 6. So what's its area going to be? What's the area?
72
Okay, 72 what?
inches, square inches.
Squared, okay. Now, I don't normally put any units in here. I just do that at the end, okay? So if we're in inches, that way we can just roll with it, okay? You guys okay with that?
Yeah, that's fine.
Okay, so x is the distance from the origin to the YY centroidal axis of this shape. We're not looking at any of these other ones, just this shape. So what would the x distance be from the origin to the YY centroidal axis of shape 1? If you look at that chart, what does it say? It's going to be your base, which is 12, divided by 2. Does everybody agree with that?
Yeah.
Okay, so we're taking this base and dividing it by 2, and that comes out to be 6 inches, right? So this tells me to multiply 6 times 72. So that would give us 432. You guys agree?
Agreed.
If you were looking at the unit on that, what would the unit of that actually be? Inches squared times inches. So this actual unit is what? Inches to the third, correct? Right? Okay, we'll agree with that. All right, so the y is the distance from the origin up to the axis here. So it's from that point up to that axis, and it's running this way. So that's going to be, in that chart, it's going to be half of 6, correct? So that would give us a value of 3. Okay, so that's the distance. That's the distance from the origin to the XX centroidal axis running through shape 3. Strictly just getting that from the chart. Okay? So now we're going to take 3 times the area. So we have 72 times 3, and I get 216. You guys agreeing with that?
Yeah. Yeah.
Okay. And again, that would be inches cubed. But remember, what we're going to come up with is an inch. So I want you to keep that in mind, that unit. Okay? All right, so now we're done with shape 1. So now we're going to shape 2. So we need to calculate the area of a triangle. The area of a triangle is 1/2 the base. I'm going to call that the base times the height, because the base is always parallel with the x-axis in that chart. So the base is 12 times 6 divided by 2. I'm coming up with 36. Does anybody agree, disagree with that?
Yeah, that's what I got.
Okay, perfect. 36. Okay. All right, so now we need the x-axis from the origin over to the y-y centroidal axis of this shape. So this is a line just like it is in that chart book on page 190. So notice it should be what? 2/3 of 12. Everybody see I'm getting that? We're coming over 2/3 of 12 to put that y-y centroidal axis in. Is everybody okay with that?
Yep.
What'd you guys get? Eight, I hope. All right. So if we get a x value for shape 2, we get an x value for shape 2, we're going to now take, for this, it says take the area times the x value, and you get 288 inches cubed. Right? So now here's where we have to think about this. If the origin of this part is sitting here, we're just 1/3 of 6 up, but the origin is actually down here, so we're going to have to take 1/3 of 6 plus 6. So we have to get 6 up to that point, and then we're going to come up another 1/3 of 6. Does everybody see that? That's where it takes a little bit of thinking. So we got 1/3 of 6 gives me 2 plus 6. So the y-y centroidal axis of this part with respect to the origin is actually up there at 8 inches. Does anybody have a question what I just did there? That's going to be the hardest part.
Can you go over that again?
Sure. If we look, there's your origin, right? Notice you have to get 6 inches up to even get to the base. Did we see that? And this guy is 6. So if you look on that chart tells you, if it's oriented like that chart, that we're looking at what? 1/3 up. So 1/3 of 6 gives me 2, but we have to come from the origin up that 6. So 6 plus 2 gives me 8. Does that help?
Okay.
Got it now?
Yeah.
That's going to be the hardest part. All right, that really will be. And once you get used to it, you'll see it's not that big of a deal.
And where did you get that 2 and 3?
These numbers,
Yeah.
I just arbitrarily called that part 1, shape 2,
Okay.
shape 3.
Okay.
That was me. I could have labeled them completely different. Okay.
All right.
I was just starting out with simplest to more complex to the most complex kind of thing. But you can, at the end of the day, you can call it anything you want. Okay.
Okay.
Yeah, that's just an ID. Okay, it's just an identifier. We good on that?
Yep.
Okay, so what we're going to do now is take, for here, we're going to take 8 times the area, and actually because that's the same, you're going to come up with the same number, right? 288. We agree?
Yep.
All right, so now we're doing the hardest shape. Now you got to look at this. The shape that's in the book is rotated 90 degrees with respect to our shape. So what you're going to have to realize now that in your book, in our figure, what we're calling X is their Y, and what we're calling Y is their X. So everything's rotating, okay? Does everybody see what I'm saying? What the book's calling X is our Y, and what they're calling Y is our X, because we've rotated the shape with respect to that chart, okay? So what's the area of a semicircle? So we would have pi r squared divided by 2, right?
Yeah.
Okay, so let's go ahead and calculate that. and you're going to get some rounding. So that's another thing. When you do centroids, I usually try to carry them out maybe 3 decimal places max. But the more you round, the more problems you're going to have, okay? So for this, I got 56. You guys check me on this. 56.549.
Yeah, that's what I got.
Is that good? Okay. All right, now watch this. This is going to be probably a little bit strange, but we know that the origin to the face of this semicircle is 12 inches, right? Based on that right there, right? 12 from the origin to that, but we're actually going to be out here. So our YY centroidal axis is out here. If you look at that chart, you'll notice that they have 0.4244R. So this distance from that point to that axis is going to be 0.4244 times 6. And we're going to have to add that number then to 12. Okay? So we're going to take 0.4244 times 6. That gets me 2.546 plus 12. So my total answer there is going to be 14.546. Questions? That's going to be probably one of the harder ones to deal with right there. Are we okay?
Are you able to just go over that one more time?
Absolutely. If you look in the book, this thing is rotated 90 degrees, right?
Right.
And they show you the Y bar going this way, which actually is, going up, is 0.4244R.
Okay.
But see, ours is actually rotated, so what they're calling Y in the book is actually X. So here's what you got to envision. Out here, maybe this will help. Out here, about right there, there's a axis running through this guy that would be the balance point of it. You see that?
Yeah.
And this distance is related by that value 0.4244R.
Okay.
But we need to come from here to that line, right? So we're going to take this distance, which we calculate, 0.4244R plus 12, and that's where I came up with this. So this distance right here turns out to be 2.546 plus 12 gives me the 14.456. Does that make sense now?
I got you now. Okay.
Okay.
Cool.
Perfect. That's going to be, really seriously, that's going to be your hardest thing. So we're going to multiply now. We're going to multiply the x times the a. And again, you can round this to a point. But the more you carry it out, obviously, the better your results are. But you can be off a little. So I get 822. I'm going to call it 562. 822.562. And all I'm literally doing is multiplying that times that. That's where I get that from. Is everybody okay? Can somebody tell me where the y value of that's going to be?
Wouldn't it just be 6?
Yes, absolutely. It would just be 6. That's correct. Okay. So everybody else okay with that? Because that's really important.
Yeah.
Okay, so this is 6. So we're going to multiply 6 times the area. And we get 339.294. Is that what you guys are getting?
Yeah, I got that.
Okay, perfect. So All right, we've done all the hard work. Okay, now comes the easy part. All we're going to do is sum that column. We're going to sum that column, and we're going to sum that column. Now remember what I said. You could have negatives in here, so when you sum them, you have to sum them algebraically. But everything's positive by the way we constructed it, so we're all good. So we're going to take 72 plus 36 plus 56.549. I got, you guys verify this. I got 164.549. We're going to sum that column. 432 plus 288 plus 822, 562. 1542.562. You guys verify that. And then the last one, 216 plus 288 plus 339, 294. 843.294. Is everybody getting those numbers? We all right?
Yeah.
Okay, so by equation, x bar distance is equal to the sum of the AXs divided by the sum of area. Now, keep in mind, this has a unit of to the third, and the bottom has a unit of to the second. So when you divide one by the other, you'll wind up with a unit of to the first. So that's how you're going to get up into inches. So this is inches cubed, inches squared, and when we follow through with that, will be inches, which is what we're after. What'd you guys come up with? .375 inches. So what we got?
Yeah.
Okay. So there's the one centroid. And then y bar is the sum of the AYs divided by area. We have 843.294 divided by 164. Okay, again, inches cubed, inches squared, and we're going to wind up with inches. I come up with 5.125. And there's your answers. So what does that tell us? Where we would balance this thing. So if I came over and drew those, what I notice is my y bar distance is somewhere about right there. My x bar distance would be possibly about right, or y bar, that's me, excuse me. This would be the x axis. This would be the y axis. And if I erased that off right there, what I'm saying is this distance here to the YY is 9.375, and this distance up to that one would be the 5.125. You get the idea? So if you cut this thing out of a piece of paper exactly, you could put your balance point right there and it should balance perfectly on it. That's what it's saying. Okay, is that making sense?
Yeah.
So which ones did we switch the X and Y on? Was it just the triangle? Or no?
We did it on here because this shape on our picture is rotated with respect to the way it's oriented in the chart.
Okay. Now,
Okay.
what was like? I see it on the chart right now. How it's kind of like a, I don't know, like a half moon with the flat side down.
Right.
If it was flipped 180 degrees, would we leave it or not?
Yeah, if it's 180, it's no different. It's just mirrored.
Okay, but if it's rotated 90 degrees either way, you just switch X and Y.
Yep, exactly.
Okay.
Yeah. And the same thing with the triangle. We got to be really careful with triangles, okay? Because what they're calling your base may be your height, okay? Just don't always assume. Here's a way to remember that. Your base on a triangle is always parallel with X, okay?
Okay.
The base on a triangle is always parallel with X, and the height's always going to be parallel with Y.
Okay.
Okay, does that make sense?
Yep.
All right, let's tackle another one, okay? Give me a minute. I'm going to redraw something. We'll do something else. This one's going to have a void area in it. So what I mean by having a void, we're going to consider it a negative, okay? So let me, give me a minute to draw. If you guys want to take a break a sec, go ahead. It'll take me a few minutes to get this drawn up. These aren't really easy to do, but this sure makes it better than not having it, I'll tell you that. So I'm going to put it, it's going to take a while to draw this, but maybe not. So I'm going to have a line running through here. Like this. Not quite as efficient as AutoCAD when it works. Okay, almost ready. Okay, I'm going to have an origin here. And call this x-axis. This is the y-axis. This is 3 inches here. This is 6 inches up. We have 3 inches from here to the cutout. And then this guy's 4 inches across. And then we have another 2 inches. Let me draw that a little bit better. Okay, does everybody see that? So we have 3 inches from the origin to where that cuts. We have this semicircle, which is 4 inch, so that's actually the diameter in that thing, right? And then this is 2 inches over. So, okay. Then this is 6, and then this is 3. Now, we're cutting this thing out, so that's not really part of it, so we're gonna have to handle that. So how many shapes do we see here? If I take a stab,
Wasn't it 3? But you would have to subtract the one of them.
right? So what I have, I'm assuming you're saying you have a rectangle
Yeah.
coming down right here, right? Agreed?
Yeah.
Okay. Triangle and semicircle. Is that correct?
Yeah.
Okay. So I agree with that. But notice this guy overlaid on top of these is going to subtract these out. But we're not going to worry about that. We're going to consider that one shape, that another shape, and then that another shape. So why don't we call that shape 1, shape 2, and we'll handle this guy, the nasty one, last. How's that sound? Okay.
Good.
All right, so we need to construct our chart. So we're going to have a shape. And we're going to have the area of each part. Then we're going to have X and the AX column. And then the Y and the AY column. Okay? So shape 1, shape 2, and shape 3. So we're starting with a triangle right off the bat. What's the area of that triangle? What's the base distance on that triangle?
6.
That's what I get. Everybody agree with that? So if you take the sum of these and then subtract it from by 3, you get this as 6. Everybody okay with that?
Now, would we switch the X and Y's on that triangle because the base is, or the longer side of it is up instead of across?
No, actually, they're first of all, they're the same size exactly. If that's 6, that's 6 also, right? So there is no longer side.
Oh, okay. Yeah.
Just remember what I said. Base is parallel with what? X.
Yeah.
Okay. So it doesn't matter whether it's longer or shorter. It has to do with which side is parallel with X or Y. Okay.
Okay.
All right. So we come up with 6 times 6, right? 6 times 6 divided by 2 gives us 18. We agree with that?
Yep.
All right. So if we look at that chart on page 190, it tells us from the origin to from the small end over, it's 2/3 of the distance, or if we were coming this way, it'd be 1/3 of the distance. So I'm going to come over 2/3 of 6. Gives us 4. Is that what we come up with? That's the distance from the origin to the centroidal axis coming this way. 4 units. Yeah. So 4 times 18 gives us 72. Not too bad, right? Not too bad. So what about going this way now? Since we're coming from the big end of the triangle, it's what? 1/3 up, 1/3 from the big end, 2/3 from the small end. So we're coming up 1/3 of this distance, which is 6. So 6 divided by 3 gives us 2. for this guy. 2 times 18, 36. You agree?
Yep.
And then that takes care of that guy. So now our next shape is this rectangle. And this rectangle is 6. He's 3 by 6. Okay, so the area is simply 3 times 6. Again, that turns out to be 18 as well. So if we were looking at the origin being here, okay, if the origin was right there on this shape, we'd be 1/2 of 3, which would give us 1.5, right?
Yeah.
But our origin is actually over here, right? So we have to come 6 plus 1.5. All right? So everybody care that? Just put your origin here temporarily, calculate what the distance is with respect to that, and then add this to it, because our actual origin is over here. Okay?
Okay.
So I came up with 7.5. Somebody have a question?
No.
Okay. So we're going to take 7.5 times 18, and that gets us 135. So all I'm doing is taking what this says, your A value times your X value, place it here. Okay? So what's our Y value? Somebody tell me? That one's pretty straightforward.
3.
3, yeah, 3. So 3 times 18 gives us 54. All right? Does that work?
Yep.
All right. So now we need to calculate the area of this thing. So the radius of this is actually 2. Does everybody see that? Because this is defining the diameter, correct?
Mm-hmm.
Okay, so pi r squared, half of that. Let's see, so we get 2 squared times pi divided by 2. What'd you guys come up with?
9.87.
Not what I got.
Oh, oops, I flipped it around.
It's all right.
6.283.
Yeah. 6.283.
Yeah.
Now, this area is not a positive area, it's a negative area.
Negative.
Figure that.
We're saying it's
Because
negative.
we're subtracting it.
Yep, because we're cutting it out. So we're drilling a hole in that thing. It's a void area. Okay, we're getting rid of it. I'm going to knock the size down in there a little bit. I'm going to crowd myself. I'm going to put him over here a little bit. 6.283. Okay, does everybody understand that now?
Yeah.
If you forget the area negative in there, you've blown the problem, all right? Because basically you're saying you have another shape in there that's positive. Okay, so we need the distance from here to here. So this guy's oriented just like the shape. And notice if that was the origin, it would be just 2. But since we're 3 over, we're going to have 3 plus 2 to get to that point. Agree?
Yeah.
So that gives us 5. So we're going to take 5 times the area. And what do you get?
Would we make that a -5 or not?
We do, because we're multiplying, you're just following rules of algebra here, right? A negative times a positive is going to yield a negative.
Yeah, but we wouldn't make that 5 a negative. We would
No,
just.
we wouldn't, because -5 would be saying we're going this way from the origin in negative territory.
Okay.
This distance is a positive distance. So you can have negative numbers. If my origin was over here, I would have negative axis. Do you see that?
Mm-hmm.
Okay. So yeah, if you make this negative, you're going to make that positive, and that's going to screw it up too. So you have to follow what's going on here, and then when you do just the normal multiplication, you know, negative times a positive is going to yield a negative number. So I'm going to get a negative 31.416. Does that sound right?
Yeah.
Okay. And then we have the y value. Now the y value is going to be that distance above, which it shows you on the chart. That's going to be what? 0.4244 of r. So 0.4244 times 2 gives me 0.849. Does that sound right? I'm taking that 0.4244r. We good?
Yep.
So we're going to take that times that negative area. Gives me a negative 5.334. Okay, so there's all your hard work. Okay, once you've done that, the rest of it's pretty simple. It's just sums and then dividing the one sum by the other. So we're going to sum that algebraically. 18 plus 18 plus a negative 6.283. I get a positive 29,717. And then I've got 72 plus 135 minus 31,416. You guys verify this. I get a positive 175.584. And then the other sum, 36 plus 54 minus 5.334. Looks like 84.666. Okay, you guys agreeing with my sums?
Yeah.
All right, so now then we just do our divisions. So we have the x bar distance is your summation of your ax's divided by your area. So we have 175,584 divided by 29.717. Gives me 5.9. We could just call it to 2 decimal places. Basically that. And the y bar is the sum of the AYs divided by area, 84.666 divided by 29,717. So that's going to give us check my numbers. Looks like 2.85. I'm just rounding to 2, so okay. Does everybody agree with that? So my y bar distance is somewhere over here. or X bar, I should say. And my other one's just slightly above, like this. That's your YY centroidal axis. That's your XX centroidal axis. So this is the Y bar. The Y bar distance here is up 2.8. Well, actually, I drew that wrong, didn't I? This should actually be down here in the void. So what's happening is here, that's kind of weird. The balance point is actually, let me undo that a little bit. The balance point is actually down here a little bit. So notice right there is where your actual balance is. So it's not even on the part, it's on the void, which that can happen. That can definitely happen. Any questions, guys? For now? I'm sure we'll have plenty of questions later on. Everybody okay?
Yeah, it seems pretty simple.
It's not, okay, it seems simple and it is, but there's always, like anything else, pitfalls, right? So you can have issues sometimes, but most of it's just geometrics, okay? It's just geometrics. So we're going to take a look at another problem. And this problem is a manufactured shape problem. So you're going to need your book, okay? So give me a sec to draw this up. And then we'll be done for today. So, all right, so what we're going to have, and this is kind of a typical kind of problem that you're going to see. We're going to have a plate. And on top of this plate, let's see, I do have a cool little symmetric tool. On top of this plate, we're going to have I'm sitting, actually, this is called an angle. Let me do a erase here. Okay. Give me a sec here to construct this. Tool's still on. Okay. Oh. Yeah, let me redraw that. Get this a little bit. My picture's not going to be perfect, but I'm going to try to. Yeah. This is a little part. Yeah. This is a part that's called an angle. So these are manufactured, and these are called legs on your manufactured part. This is a plate. So let me put some dimensions on here. This plate, usually a plate is indicated with a P through an L like that. Our plate is it's going to be 6 by 1 inches. Okay, so we've got 6 inches by 1 inch plate. That's what this guy is. And this is called a leg or an angle. They usually call it like that, and then they'll say 3 by 3. In this case, we're going to have 3/8. So what that's saying is this leg is 3, that leg is 3, and this width here is 3/8. Okay. Our plate is 1 inch. This is supposed to be perfectly symmetric on that thing. Let me see if I can get that little piece better. It's kind of hard to draw this thing, so I think you get the idea. So also those have been, those little pieces, we're going to fasten those. We're going to fasten those on there so they would be sitting flush. Okay, so everybody get the idea? This would be sitting on that. It's either welded or it's bolted in place. We're going to call this piece over here, this is where the origin is. And the x-axis is going to be running up like this, and the y-axis is going to be running up the face of that angle like this. Okay, so there's that. This is x. This is y, okay? What does anybody notice about the way these are arranged? There's something on here that's really important. We have what's called symmetry going on. So if this is 3 and that's 3 and this is 6, you should probably be able to tell me right now that the axis running through here would be the balance point, okay? This balance point is going to be a little bit harder, but it's going to flip up a little bit in here. So we're going to have the YY centroidal axis. The YY centroidal axis will be somewhere here, but I guarantee you this one should have a value of 3 coming this way, okay? Everybody okay with that? We good?
Yeah.
Okay. So our plate is real simple. We're going to consider that a rectangle, but we have to look up these guys in the chart. So I'm going to call this guy shape 1. We're going to call this shape 2, and we're going to call this shape 3. Okay? So we are going to set up our table, shape, area, x, ax, y, and ay. Okay? So we're going to have shape 1, which is a rectangle, 2, which is the left angle, and 3, which is the right angle. And the cool thing is there's symmetry in these guys, so kind of what's happening left will also be happening right. Okay, so we'll see how that works. Let's attack the plate first. That's simple. So this guy's 6 inches by 1 inch depth. So what would be the area of that?
Six.
Yeah, pretty simple, right? And the x would be the distance from our origin point, this guy, over to the center of that plate, which is going to be half of 6. So that's just simply 3, right?
Yeah.
So area times x is 18. Okay. What about y? The plates,
0.5.
right? 0.5. So 0.5 times 6 gives us
3.
3. Okay, that one's pretty simple. So now we have to go into the appendix. Okay, so we're going to go back to the appendix, Appendix A. And you notice when you get into Appendix A, which starts on 593, you have all these what we call engineered shapes or manufactured shapes. So it starts out with W shapes, which is the same thing that most people would call an I-beam. And then we have a little bit further down, after you go through the W shapes, then we get into what are called C shapes. Okay, they're kind of like a half I-beam. And then we're going to get into angles, okay? And you got a lot of numbers on these things. So we are looking for an angle that is what's called a 3 by 3 by 3/8. So notice in the shape column, they have different values. So if you go to page 610, 610, did we see that? You can find a 3 by 3 by 3/8 in there. Is everybody finding that on page 610? Everybody okay with that?
Where is this at?
On page 610 in the back of your book.
Okay, I'm on that page. Okay, I see it.
See it now?
Yeah.
Okay, so if you look, first of all, there's a little diagram that shows you stuff going on in that. That's going to be critical. We're going to look at that. We'll have more time to look at this in class. I can help guarantee it. But if you go down the shape column, you find they're categorized by angle distance, right? And you'll find down towards the bottom, about 1/3 from the top up, it's looks like from bottom up. Looks like you'll find the 3 by 3 by 3/8. Is everybody finding that one?
Yep.
And the way these charts work, they work together. So page 610 and 611, we're talking about the same angle. So you just read across this thing from left to right, okay? So there's all these properties X, properties Y. We'll get into these. The main things we're looking for is going to be the area. Everybody see the area column? And then under the XX axis, you'll see a Y bar. And then if you go over to page 611, you'll see a YY axis. And then under that, you'll see an X bar. So we're only looking for 3 pieces of information from this chart. Now, when we get into moments of inertia, we're going to be looking for a lot more, but that'll be next week, okay? So if we look at the 3 by 3 by 3/8, who can tell me what the area is right off that chart?
$2.11.
2.11. Everybody agree with that? 211. And what's true about 2 and 3?
Same
Same
exact.
angle, right? So we can go ahead and put that area down there. Right? That's kind of nice. When you start using these things, these charts make it real simple. Okay. So go up to the top and they show you that little angle. They show you this angle up top, and they show you a YY axis running down through the angle like this. And from the back of that angle over to the YY axis, it says X bar. Everybody see that? So it's showing you that we're going to measure that X bar distance this way to the YY axis of this. Okay, so that would be this X distance that we're looking for. So we're going to go to the YY axis over on page 611 for the 3 by 3 by 3/8. And what would be that X bar distance? We're on page 611 now because we had to read across the row. What do we get for that X bar distance?
Would it be 0.884?
It would be, right. So it's 0.884 from here over to the Y bar. Okay, do we agree that? So we're going to write that down here. Now, it won't work the same way for this one because that's coming this way, but we need to come from the distance. For this one, it's 0.884 going this way because we mirror imaged it, but we'll need the distance from the origin here. So we'll handle that here in a minute, okay? All right, so we're going to take the 0.884 times the 2.11. What'd you get? I get 1.8.
1.86. 6.5.
Yeah, that sounds good. 1865. Now, the y, notice they show you that little chart. They show you the y bar distance is from the bottom of this face up to the yy, or the xx axis. And since we're actually coming from an origin down here, we're going to have to take 1 inch plus whatever that number is. Now, because these guys are what we call equal legs, the x bar and the y bar distance are going to be the same. But if we look under the xx axis for that y bar distance, we're going to see that it is also 0.884. Okay, so from this point up to that axis is 0.884 also, because these are equal legs. If they were not equal legs, you'd have different values x and y. Okay, so we've got 0.884 up, but we're coming from an origin which is down here, so that's going to be 1 unit plus that 0.884. So y is going to be 1.884. Did everybody see how I got that? We all right?
Yeah.
Okay, so we're going to now multiply the y times the area. .884 times an area of 2.11. Came up with 3.975. Okay, 3.975. Okay, we ready to go to the shape 3 now?
Yep.
Okay, so shape 3 is identical to 2. Area is the same. This guy's mirror image. So what we see, this is mirror image. This distance here is the same thing as it was here. So that 0.884 is here, but we need to reference it to this point, the origin. So if we take 6, gives me to that face, and we subtract the 0.884, that'll give me what the x value is. So again, if I go over 6 and then back the 0.884, I'll be right where I need to be. So I'm going to take 6 minus 0.884. I get 5.116. Questions? Anybody? How I achieve that? So we now take the x value times the a value. So we have 5.116 times 2.11. And that gives me 10.795. You agree with that?
Yeah.
All right, so who can tell me what's going on with the y? So remember, we're coming from this face up to that XX centroidal axis of shape 3. So what would be true about that?
Be negative.
No, wouldn't be negative because we're going positive. We're going this way, right? In order for it to be negative, you'd have to be going down. Okay, so just think down is negative, up is positive, and right is negative, left is positive. Or I'm sorry, reverse. Right is positive, left is negative. So we're going up this distance, so it's a positive number. But what's happening is it's going to be identical to what's happening in 2. Because if you remember, we said from the back face of this up, it was the 0.884. This is also to the same point, 0.884. So even though we mirror image this, it didn't affect what's going on in the Y there. So if we're coming up from the origin, that's going to be 1 inch plus the 0.884. So we're going to also have 1.884 here as well. So notice the Y's are the same in this because they're sitting on that plate. So when we multiply the Y times the area, we should come up again with that 3975. So there's all the numbers that we need. Okay. It's a little bit more difficult. You're going to have to work with us, but Thursday we're going to have plenty of time, okay? So if you're not catching this now, you'll definitely get a handle on it on Thursday, okay? Are we okay?
Yeah.
All right, so what we're going to do now is sum the areas, sum the AXs, and sum the AYs, and we're going to solve this, okay? So 2.11 plus 2.11 plus 6, I get 1022. 10.22. You guys verify that. Then I'm going to have 18 plus 1.865 plus 10.795. And that gets me 30.66. Excuse me. And then the last one, 3.975 plus 3.975 plus 3. And I get 10.95. Anybody see any mistakes? Anything I've got?
No.
So to get the centroid, X bar sum of the AXs divided by sum of the area. AX is 30 rather, 0.66 divided by 10.22. Whoa, what did we come up with? Exactly 3. Does that make sense? These things are these guys are symmetrically aligned on this. So this thing has to be 3. If we didn't come up with 3, we probably had a mistake, okay? So that makes sense. Y, now Y is going to flip up here somewhere depending on how long that angle is. We might find Y actually above this. We'll see what happens. So we've got the 10.95 divided by 1022. I get 1.07 inches. So what that's telling us is that that axis is somewhere up here, okay? It's not above it. It's somewhere coming through the angle, and the other one's right in the middle. Think about this. What would happen if this went to a larger leg this way? If this then went from a 3 to, let's say, 6 or 5, what would happen to this number right here, theoretically? What do you think would happen? Would it get closer to the origin, or would it get farther away from the origin? Anybody take a guess? If this part pushes out further, that's going to raise this axis up and up and up. So you would see this number grow. If that change this direction on both sides, this would not change at all, okay? So you kind of can start to see logically after you get into these guys how this all works. Okay, but you just have to do those homeworks. Okay, anybody have any questions? Because that's pretty much all we wanted to handle today. Anybody? Max, you good on this for now?
For now.
All right. Michael? Maybe not there. Irvin?
For the most part, yeah.
Okay. It's just, it's something that you just have to do, okay? You just have to go through them. And we're probably going to have, you know, quite a few questions is my guess. So what I want you to do is the assign problems on Blackboard for this section. And I think there's like 14 problems, something like that. So they are a combination of different types of problems. So the first, like problems 1 through 7 are the simple composite shapes. And when you get into problems 8, 9, 10, 11, those guys begin to get into the engineered or the manufactured shapes, okay? So tackle the 1 through 7s first, okay? So you get a handle on what you're doing, and then we'll look at those other ones. Also notice some of them are in millimeters, some of them are in inches, so just kind of watch that. And also notice where they give you the origin. So origin is given to you in all cases. Number 4, by the way, you should have negative values for x. Okay, so for number 4, you should have negative x values. But okay, any questions then?
No.
I got
Okay,
a
I'm
quick
gonna.
question.
What's that, Mitch?
So when you're rounding your answers, do you want specifically 2 decimals, or would you care if we just added it out? Because like my thought is like for AX and then AY, if I did like 1.87 and then 10.8, would
Yep.
that drastically change it, or should I just keep it like how it is?
Not real. Most people would probably display these to 2 decimal places. So I usually will work at a higher range up in here. I might go 3 decimal places over, you know, when I do this, but when I get done with the ultimate answer, I typically round it to 2. Okay. If you want to float it out to 3, that's fine. Sometimes I do. I mean, technically that's a better number, right? Balance is, you know, closer, but 2 to 3 is fine for your final answer for sure. Okay.
I appreciate it.
No problem. Anybody else then? All right. If not, I'm going to go ahead and stop the recording. I'll get this recording formatted. I'll have that put out there today. And then Thursday, we'll be available to answer questions. I'll be here tomorrow in office hours from 8 until 1. So you can always shoot me an email if there's questions or set up a Zoom conference. Okay? Other than that, I will see you guys on Thursday.